Welcome, everybody, to an exciting, important conversation about bias in AI. We'll be diving into things in just a moment here, but just to kick off, I want to do a quick introduction of what kind of brings us here today. So my name is Jacob Smith. I'm joined by my right hand, Ryan Robinson, who is probably not on my right side, but say hi to the people, Ryan.
Hey, everyone.
And we are here representing an exciting community called Collider that is essentially a community of technical professionals, so data, software, and other engineers and professionals who are using cutting-edge technology to solve real-world problems. It's all about collaboration and problem solving. If that sounds like you, we'd love you to be involved. Join our Slack channel. Connect with us wherever we're at. We will fill you in the chat in just a moment and how you can stay involved. We're here representing an awesome company called Altimetrik. Digital transformation is the name of the game, which basically means we help companies stay ahead of the curve with the ever-changing landscape of technology. And one of our speakers is representing Altimetrik as well, which I'll get into in just a second. So again, today we're talking about bias in AI and machine learning algorithms, how to identify where prejudiced assumptions may sneak into the equation, and how to mitigate so that you can be ensuring that you're making good decisions with your algorithms. We're joined here today by a couple of very smart and knowledgeable gentlemen, Antony Martin from the Altimetrik team, as well as Chris Penny from Mythics, Inc., who are going to be diving into, they can introduce this in a bit more detail, but they're going to be diving into some specifics about what I just mentioned. I also encourage you to check out their most recent presentation that they did with our team that was all about how AI enables computer vision. Which was a really exciting session maybe a month or two ago that I just dropped the link in the chat, so be sure to check that out as well. And before I pass it off, I just want to encourage everybody, this is intended to be interactive, collaborative, so please feel free to drop questions in the chat as we go, and we're going to leave time at the end, not only for lingering questions, but also we're going to be asking folks to share how what you learned today might apply to what each of you are doing with your own projects. We'd really love to kind of hear from whoever's interested in sharing. So something to think about as we go along. And so without further ado, Antony and Chris, take it away.
Hey, I'll do a quick introduction. Guys, my name's Chris. I'm with a systems integrator, Mythics, Inc., Incorporated. I'm based out in Austin. The name of the game for us is digital transformation as well, but the space we play in is mostly migrating customers from on-premise workloads to cloud-based workloads, and Oracle, Google, and a few other the big cloud vendors. But I am excited to speak on this topic. I've got some experience with bias in AI, and I think the goal of this presentation, first, we wanted to talk about the multiple contexts in which you might hear of bias in AI, because it's not just systematic prejudice bias. The term's thrown around a lot, so we're going to discuss those other the other contexts in which the term's thrown around, and then we'll dive into some code and some questions. So I'll pass it off to you, Antony, on that note.
Yep. Hey, welcome, guys. So again, I am a deputy at Ford Motor Company. I'm an employee of Altimetrik, and Ryan and Jacob are my colleagues. So I work in electric vehicle space, involved heavily in big data. So every day in, day out, I work with electric vehicle data, do the data analysis, glean some insights. So I got a bit of experience in machine learning and AI. So as Chris said, I'm very excited to talk on this topic. So without further ado, again, as Jacob said, right, if you guys have any question, we want this session to be as much interactive as possible. If you guys have any question, please do stop us. And we can address as and when you have one. So Chris, take it away.
Awesome. So before we dive into AI and bias, let's make sure we have like a common language. And when we're referring to these terms, make sure we're all on the same page and singing the same song. So the first slide we wanted to do, what is machine learning? And I know we've got a multidisciplinary software heavy crowd. So I wanted to provide an interpretation that I think intuitively makes sense for a lot of the members of the crowd. And that is an AI model or a machine learning model is really just a software model that makes a prediction, but the way in which the software model is designed, it moves away from rule-based models to actually learning from data, learning from experience. So in that sense, most of machine learning, or at least the machine learning we're going to talk about today, is based on pattern recognition. What patterns are recognized in the data? Another interpretation is based on this definition, which I like. This is from a famous British statistician. It's all models are wrong, but some are useful. And what it's referring to is that models are really just an approximation of reality, right? So a model's contingent on two things. It's contingent on the data that it's fed with, because those are where it extracts and learns the patterns. Those are where it does the pattern recognition. And it's also based on the model class. So the way in which the model sees reality is very contingent on those two factors. And this is important because when we get into the bias topic later, we'll talk about how any kind of inconsistencies or redundancies or noise in any of those two areas is going to propagate and percolate when the model's making predictions. So you can go to the next slide, Anthony. This is another important thing to remember, just to make sure we're on the same terminology. Machine learning models are useful, or they're most useful when making predictions when the future looks like the past. The past, in this sense, just represents the data that the model was trained on. So this brings up some interesting questions, right? And one of them, for example, is what happens with rapidly changing fields, right? For example, maybe the finance sector or any kind of social media app where trends on social media rapidly evolve and change based on some larger context. Another thing is what happens when the future looks different from the past. These are all interesting questions that we'll dive into later in this presentation. Before we jump into that, though, I do want to mention there is one term in machine learning. It's called IID. It means identically and independently distributed. So this is an assumption that we make with models. And that assumption is essentially around this. We're assuming that the data, or at least each row or each instance in the data, we're assuming that it's independent of other examples in that data set, and we're assuming that it comes from the same distribution. So it's drawn from the same probability distribution. When these assumptions are not met, we have to, as modelers, as engineers, or as data scientists, there's certain special, I guess, techniques and other processes that we have to do in light of those assumptions being violated. So you can go to the next slide, Antony.
Yeah, with that common language understanding, right? Let's just talk about like what bias is. Like from our understanding, right? From a human perspective, we think bias as like favoring someone unjustly, right? Or inversely, like it also means discriminating someone, right? So that's what we all define what bias is. So it's integral to know like why this is happening. Like nobody wants to be a bad person, right? Nobody likes to be called like he is biased or he is a discriminating person. But why does it happen, right? It is because of the most laziest part of our organ in our human anatomy, which is our brain. That bugger is lazy, right? After a certain age, he does not want to learn, or he does not have the same curiosity to learn the new experiences, right? Rather, what he tries to do is just, when he sees something, smells something, feels something, right? One, he tries to associate it with the experience that brain remembers from the past. And the second thing is because, we have 567 megapixel camera, like 2 of them in our eyes, but our brains are not capable to process like all the information that we get, right? So it simplifies, like how often, right, do you guys run into someone in a mall like, or bump yourself like in the edge of a bed, right? No, our eye sees it, right? But still, we go hurt ourselves at times because we oversimplify things. Our brain is unable to process all the information that we have. It only selects few information from here and there, simplifies the big complex world into a smaller narrative so that it's easily processable by the brain. So that's what happens, right? So we have an experience in the past, and our brain simplifies stuff. When these two things put into together, right, at times unknowingly, right, we end up in being a biased person. So if any one of you think that you are not biased, then you are wrong, right? Every single human being, right, is biased in some way or another. It's just that at times we don't know, or at times we know, but then we hold it back until we get more experiences, right? So the people that get into trouble is when the people who do not realize that they are biased, and then they speak out way too quickly than they think, right? So let's take the same principle and apply it in computer learning or artificial intelligence, right? So artificial intelligence and machine learning does the same thing. It does the pattern recognition. It wants to understand the data. Like you can give a complex set of data, but it wants to simplify it in a mathematical space, if you will, so that it can tell a story. It can predict something out of it, right? So given 200 parameters that you have, right, it wants to simplify it, understand from it, and then predict, like, if he or she is a good or bad person, for example. So does it mean that a machine is discriminating? No, that's not in the nature of a machine, right? A computer cannot discriminate. As Chris pointed out, right, machine learning is just, the way you train is like take a point in time in history, represent that in terms of data, which is from the point of human being, right? So all the data, like I see history as something, I represent it in a format. Again, given that I'm a flawed person, my brain is flawed in thinking, right? I'm a biased person. So when I put together data, it's kind of biased in a way, right? I might not realize that. The model, all it does is it just reflects what some of the biases that we have in the data, right? And there are a few other cases which from which the bias could propagate. For example, the systemic, the bias from the model itself, or the tuning that we could do in the model, right? There are other parameters, but a machine by itself is not capable to discriminate someone, right? It just reflects what it had learned from the histories. Though we want our machines to assume that the world is ideal, like we are in the Garden of Eden, and we wanted to predict something nice and beautiful and not discriminate anybody. But we as humans have to be very conscious in providing such a data to the computer so that it can learn from it, right? If you just give the data from the history, which is again our perspective of what the history was, which will have some bias, the machine is just going to resonate it. So one thing that any ML and the AI engineers should realize that is that any data that they get is in some shape or form is biased, right? So they should recognize this fact and then try to build off of it. So then what does a bias means to a machine, right? So for a machine, it's just an error, right? It was trying to predict, like, for example, if I want to predict like a white male with a beard and with a beard and a hat is Jacob Smith, right? If the model ends up in predicting it as like Chris, then yeah, we may say that it has a bias, right? But to a model, it's just a prediction error. So what are different types of prediction error? Like as I highlighted here in the deck, there are three forms: reducible, irreducible, and biased. So reducible and irreducible errors are variances, and so any model that we build, right, it would have these two factors, a bias factor and the variance factor. And it's up to the engineer or the data scientist who's building the algorithm based on the use case. They have to determine if their use case warrants for weightage on a bias in some case, or do they want their model to be highly variant, right? So bias and variance are inversely proportional. For example, if you increase the bias, then you can reduce the variance. If you increase the variance, then the bias would be reduced. So what is bias itself, right? So put it in a ML term or artificial intelligence term. Bias is nothing but the ability of the model to learn all the features in the data set and then be able to predict something, right? So when there is a high bias, then that means that the model is favoring a particular class, right? For example, we might have cat, dog, bird, or whatever species, and in every single instance, our model is biased to predict whatever input that we give as a cat, right? So it's basically like how well the model understood or able to understand the functional form of the independent data and then be able to predict. So variance is something where our model is able to generalize the data enough, right? It was able to learn super good with the test data. But then when you present it with, or when you put it in practice in the real world, it's making bad predictions. Again, example, if you build a model for, let's say, for Americans, right, just by their features, you tell them like either, where he could potentially live, right, based on their slang, their beliefs and whatnot. So if you build such a model and give an input of a feature of an Indian like me, then the model is going to, of course, not be able to predict because the model learned very well about all of American culture, the races, everything, but it learned so well that it's unable to predict anything outside of the given feature, right? So that's kind of the variance factor. So you can, it's upon the engineer to based on the use case to assess what they want to control. So in some cases, the ideal case is that we want to bring down both the bias and variance to the lowest number possible, but that may not be always possible. And in some case, we may want the model to be a little bit more biased than we want, or in some case, we want the model to be a little bit more highly variant compared to the bias factor. Right. So with that, Chris, do you want to add anything?
Yeah. The next slide, I showed the trade-off.
Yeah.
So yeah, to jump in where Antony said, error, right? It can be decomposed. There's a lot of different decompositions of error, but a useful framework is systematic error and then random error. The random error is the noise in the data, right? So in order to reduce that, I mean, that's kind of irreducible unless you have a bigger data set. With smaller data sets, you're likely to have more noise just because there's less samples. But what we want to focus on is systematic error, and this is what Antony was talking about. Systematic error is composed of two things. It's bias and it's variance, and there's usually a trade-off. So when we increase one, we're usually decreasing the other, and vice versa. Optimal model performance is somewhere at low bias and low variance. And it's important to remember that these two quantities, they're not necessarily linearly related. So if you increase one, doesn't mean that you're going to get a proportionate linear decrease in the other. The relationship's more complicated than that. But ideally, what we do is we want to tune the model such that it has low bias and low variance, because that's going to give us the lowest amount of model error, and that's going to give us the best generalization performance. And when I say generalization performance, I mean the best performance on new and unseen data. You want to go to the next one, Antony? So here's an example of some of the different bias and variance ratios. You can see those three. I mean, these are simple models. They're in 2 dimensions so that we can visualize them. But you'll see on the left, it's the underfitting model, which is a high bias model. Underfitting essentially means that our model is making too many assumptions, right? And it's too simple. So in learning the relationships and based on the assumptions that it's making, it's assuming very simple relationships, and that's what it's encoding in the model. And that's also what it's essentially projecting on new data. Remember, models are really just approximations of reality. So the approximation of reality is too simple and it's not going to perform well. Then we could have overfitting, which is the case on the right. That is where you have high variance and you have low bias. In this case, the hypothesis, which is the model, it's too complex. And that just means, in a nutshell, that it's learning some of that noise. If you remember on the previous slide, we talked about systematic error and random error being that noise. If our model is picking up on that noise, which is very specific to that data set, think of it as like idiosyncrasies, and it tries to project that on new data, obviously there's going to be a problem and there's going to be some error. So the best model is really a compromise, which is low bias and low variance. So the next question naturally is, how do you tune the bias variance trade-off? And Anthony, feel free to jump in. I've labeled a few on the left. There's two things you can do. One of them is you can tune the feature space, which is the amount of predictors. By adding extra predictors, you are increasing variance and decreasing bias. And then by decreasing the amount of predictor variables you have available to you, you are increasing bias and decreasing variance. Another way is regularization. That is a technique that you can use. It's kind of outside the scope of this presentation, but for a curious reader, I encourage you to look into that. Most of these models have regularization built into them where you can tune that parameter and you can control the bias variance trade-off. You want to jump in, Antony, and add anything?
So the one thing that I want to add is like feature engineering, right? So to splice it down in terms of English. So in the model, we have to be very conscious, right? We might get tons and tons of data, but we need, as an engineer, we need to assess like which data element do we really need for these use cases, right? So again, having a lot of data always helps in better advance a model, right? With every new feature or column that you add in the Excel, in a PowerPoint, you would be able to explain or tell the story a little bit more better. But unknowingly, what we end up also doing is that we'll end up in creating a bias. For example, if we want to measure the success of people in America, right? So how do you do that? So if you use salary as a success, right? The amount of money that they make, and if you want to use that as a success, that's fine. But so that should be just based on the position that they hold, the number of experience that they have, and the education that they have, and the money that they make. But the moment you add the gender feature or the functionality in it, which is not totally necessary in this case, then our model would end up in biasing towards like, okay, male colleagues make more money than female colleagues, right? So that sort of gender bias would automatically come in. So our engineer should be, should understand the data set that he or she is getting, and they should carefully pick and choose that the features or the data elements that they want to use for the purpose of building this model. Some of which is part of feature engineering.
And real quick, just to piggyback off that, you do a lot of that in the exploratory data analysis phase. So that's one of the first phases of any ML project, where you're exploring the data, you're seeing what values exist. And then you're even making, I guess you're bookmarking that, hey, this predictor variable could be problematic down the road, but we will have to debug it later. And we go into some of those debugging techniques later in the presentation. You want to go to the next slide? So this is just, it's really the same chart as before, but maybe a little bit better, and it shows how the relationship between bias and variance isn't linear, and that you can have low bias and low variance, and that both quantities aren't necessarily increasing or decreasing at the same rate. The most generalizable model, as you can see, is in that middle band. That's going to have low variance and low bias. You want to go to the next slide now? So we wanted to, I don't know if we need to touch up on imbalance classification too much, just because we are crunched on time. So I think we can go into this with the code blocks and the Google Colab code. Is that fine with you, Antony?
Yep.
Okay, let's skip this one, and then we'll go to responsible AI, bias in AI. So this is where we loop back to some of the things we talked about in the beginning of the presentation. And we talk about, hey, what does it essentially mean when AI, or essentially like a model, could learn some of the systematic bias or some of the prejudice bias, like gender bias, age bias, racial bias in the data set. As I mentioned before, the model's trained on data, and the model makes an approximation of reality based on that data. And it also too depends on the complexity of the model. So the model makes assumptions with that. But if there is bias in the data, and sometimes the bias is easy to spot, you know, like Antony mentioned, if you have a predictor variable that's gender, then, you know, it's likely that there could be some bias in that, really depending on what time period you collected that data. For example, if you're looking at making a prediction model on maybe data from like the 80s or the 70s, where women weren't given, I guess, the same access to opportunities, then a data set from that time period likely will have some bias. And then even today, with a lot of the data sets, there's still some of that systematic bias and that lack of access to opportunity, which will kind of reverberate itself and be found in the data. I went right here at the bottom, I went into some of the specific sources of bias in AI. One of them being measurement errors. That is, if when you're recording data, if there's an error in recording it, there could be an error with whatever tools or systems you're using to record that data, or if you're maybe doing it, hand coding it, there could be a hand coded error in there. Another source of bias is corrupted data. And then a third source of bias, which we want to touch up on and talk about a lot, is lack of representation or diversity in data. Many data sets present a unrepresentative view of a population. And you can also have subgroups and subsections of that population being underrepresented in the data. And I'll give you an example. A good example is that most of the early facial recognition data sets, if you like deep dive into those data sets, you'll see that 80% of the faces in those facial data sets are like Caucasians. And I think 75% or more are males. So that's going to bias the data set in terms of performing better, maybe on that specific subgroup, and not performing as well on other subgroups like minorities or women, or even, you know, both, right? If you're a woman minority, then you're going to get probably the worst performance out of all. Anthony, you want to jump in and maybe add to any of that?
Yeah, so on the lack of representation, right, it's very important to collect data from a huge multiple source, right? So you just do not want a person or a team of, like, you know, maybe, you know, 3 or 4 Indians or maybe 3 or 4 Americans joined together to collect the data. We want diverse demographic personnel to collect the data for the model to learn from, because the diversity in this case is very important. As I said, each of us, you know, I'm an Indian, and like an American versus Japanese versus Chinese, we all bring in our own diversity, our own understanding of what the world is. So when we all collect the data, right, we, in a way, we kind of pretty much approximate what the real world is, right? Instead of, if we just have like one group of people, you know, collect the data, then we only address part of subgroup, which, you know, Chris kind of touched upon a little while ago. So it is very important to have a diverse group of team or teams to collect the data. So that is the most important thing in any machine learning, right? 80% of the work is in collecting a diverse, rich data and then having a clean data. That is 80% of the work. The rest 20% is simple model building.
Right. And then to jump in, the final, I guess, main source of bias in AI is data access. And a good example for that is that most of the language models today are trained on English data sets, because the internet is mostly consisting of English data sets. So these language models will do a lot better when it comes to you know, English language and English language data sets than they would another language, right? So that's another example of how kind of bias creeped in. And that's just because of data access, right? I mean, the internet, like I mentioned earlier, is mostly English data sets. And then with the lack of representation, diversity, a lot of those early facial recognition data sets were mostly Caucasian and male. So we could go to the next slide. This is, well, yeah, I guess the two types of bias, this ties back into the data diversity. There's systematic bias, and that is, let's say if a data set's collected from a certain time period, then it could reflect maybe certain prejudices or lack of access, and then sample bias. And that goes into whoever is maybe doing the sampling, whether it's automated or whether it's a person doing it. If they're collecting data that doesn't accurately reflect or represent the group or the environment the model is expected to run on, then you're going to have errors down the line. And some of those errors lead to big reputation challenges for big companies. So a good example is I read this one research paper where there was gender bias in a X-ray imaging application where it was doing a lot better on men for detecting thoracic cancer than it was on women. And then there's even policing. A lot of those early policing data sets, they were almost disproportionately sampled to have many like non-Caucasians. So those sets obviously did better on those subgroups and subpopulations to the point where it led to some inferences that were almost perpetuating, the systematic and sample bias. So we can jump to the next slide. So then the next question is, with all these woes and all these problems, what do you do, right? And there's a very active area of research in this right now, and it's called model explainability and interpretability. This is essentially the solution, or at least the best one that we have right now, to addressing some of these issues. So interpretability, I've defined it based on that article, Explanation in Artificial Intelligence. And interpretability is the degree to which a human can understand the cause of a decision, right? Another definition is the degree to which a human can consistently predict the model's result. This is important because when models start misbehaving or when they start acting differently than how we intended them to be, decision makers, stakeholders, data scientists, we're going to have to be able to explain why a model is making this prediction or why a model is making this decision. The image on the right, we go over this in the code block, so I'll go over it briefly right now. It's just a bar plot of directional feature contributions where it shows for a particular sample, and that sample is going to be example number 182 from a data set. The prediction was that this is the Titanic data set, by the way. The prediction is that they weren't going to survive. And then what this chart does is it shows why did the model lead to that prediction, right? And it looks like the two main reasons for the model leading to that prediction were one, the gender, male, and two, the age. So systems like this are important for how we can debug if a model is biased towards a certain group, like a certain gender, or towards a certain age, or towards a certain racial or ethnic group. You can go to the next slide. So another thing we're doing, an active area of research, or maybe not so much an active area anymore, is interpretable models versus black boxes, right? So in the case of business decisions that need to be made, there's usually often a incentive or there's a pull to have interpretable models because these can be easily explained, these can be easily analyzed. If you have a governing watchdog or some kind of regulatory committee and they're asking, hey, why did you guys do this? For example, if it's a fraud detection application, they can easily explain the conclusion or how they got to this conclusion with these kinds of models. And examples of these models are linear models, decision trees, k-nearest neighbors. And then you have black boxes, which are harder to interpret. Ironically, the black boxes usually are better performing models, so you'll usually get better performance, but at the cost of interpretability. They're going to be the ones that are harder to explain what's going on just because these models are a lot more complex. And examples of these models are support vector machines, ensembles, and neural networks. What I have on the right is a decision tree, and this is for a flower classification app. It's a pretty basic data set. It's anyone that's messed around with machine learning should have has probably encountered this data set, but it predicts what a like what for a sample, what kind of flower it will be, right? So either a versicolor, a setosa, or an iris, and the decision tree shows you how it came to that conclusion, right? It shows you that, hey, if for example, the first node, if the length is under 2.45 centimeters, if the petal length is under 2.45 centimeters, then it's going to classify it as a setosa, versus if it's over that, then you're going to move down the tree. So it's a very interpretable decision-making process. And Anthony, you can go to the next one if you want real quick. This is more on model explainability and interpretability. Some of the tools used for the curious reader. These tools are in Python, but I think they might be in some other languages too. Lime, which it uses local models for interpretability. Then you have SHAP. SHAP's interesting because it uses game theory. I don't know if anyone's into economics or game theory, but it uses game theory in order to arrive at how it determines feature contributions. You have TensorFlow. Those are three of the tools that I like to use personally. And then some of the techniques I mentioned used by these libraries are directional feature contributions, partial dependency plots, and local surrogate methods. And we can maybe dive into these with some of the code, but I do want to leave some time to go over that. So the next thing, this is probably the last slide. I'll run through this. This is MLOps. Anyone interested in deploying machine learning at enterprise level or with their company is probably going to encounter this. This is somewhat of a burgeoning new branch. It's really the intersection of DevOps, software engineering, and machine learning. But this goes over the entire model pipeline, including the feedback loops. So if you're doing machine learning at an enterprise scale, you're probably using some of these software development paradigms like continuous development and integration, and you're probably deploying these machine learning models via containers and a container orchestration tool like Kubernetes. But this process is important as a machine learner or as a data scientist. Since there's so much automation, you have to have occasional health checks to make sure that your model's not biasing, right? Once you have a turnkey solution, it's important to monitor the health of that. And what that means is you're going to have to retrain the model, right? If you find that your model performance starts degrading over time, maybe because the data it's being exposed to is different from the data that it was trained on, you're going to have to retrain the model. Or if you find that your model is actually biasing or maybe a specific subgroup of people where it's not performing as well on that group as it is another group, and you're going to want to retrain the model with new data, or you're going to make changes. And this whole process, MLOps, just discusses that loop of retraining your model and then redeploying it, and then retraining your model again and then redeploying it. But Anthony, you want to go ahead?
Yeah. So that is the last point that Chris mentioned is very important. Like unlike a Java function, right? If you want to add A plus B, like it's a rule-based function. So no matter how many years it takes, that function would work. That's not the case with the model. Our model will decay eventually, right? It's like an apple. At some point in time, it will decay. So it is very important for a data engineer or a data scientist or an ML engineer to keep an eye on the model performance and have a continuous feedback loop to train the data, have the model trained continuously so that the model is up to date.
Yeah, and that frequency is going to depend too on what industry you're in. If you're in like a finance industry, then where the data is changing a lot faster, you're probably going to want to retrain it maybe once a week or maybe once a day, depending on. It also depends on what your financial constraints are too, right? Because a lot of this is cloud deployed, and whatever your footprint is, that's going to consume resources and money. But this is, I'll give you an example of a good one. Say you have like some kind of social media app, right? And there's maybe, or you have a wine tasting app, for example, and your model was trained on the popular wines at the time, which was like mostly red wines or mostly a certain kind of wine quality. Well, for whatever reason, the popular wines of the day change maybe like 6 months down the road, then your model's performance is probably going to degrade on maybe the new set of wine, right? Because there's new features, there's new feature combinations. You're going to want to retrain your model on that new data set so that it's accurate. So that's a simple example. But I think we should jump into the code real quick and then answer some questions after that.
All right. again, so please do interject and ask any question that you may have. So the data set that I'm going to show is basically a financial data set. We have some a bit of information about bank customers. All we got to do is predict if we can sell a particular banking product, in this case, like term deposit, to the customer, right? So I'm going to jump through all the pre-processing techniques and just jump into bias section. Again, I'm using a very simple model here, like logistic regression. This is maybe the this is like a kindergartner model in machine learning, right? Anybody who wants to learn machine learning, the first model they probably would be building is this logistic regression. So we have this data set. It has some like 36 or 50,000 records, I don't know, and it has only two classes, right? No, are they a potential customer or not, right? So 0, 1, 1, true or false. So our goal is to build a model to correctly identify the customers, or have the model learn the feature enough that it can predict who would be the targeted audience for this new product. So what I'm using here is like a grid search. So let me explain it with this. So some of which we kind of touched upon in the presentation, right? So what I'm doing here, right? So though it's a logistic regression model, there are a lot of parameters that goes into this model, and each of those parameters in some way or another affect the performance of the model. So in this case, what I'm doing is I'm doing the performance tuning. I'm trying to pass like a bunch of parameters to this model, and I'm creating multiple models on the same data set to understand like which is the best performing model, which model gives me the absolute best accuracy score, right? So if you see here, right, there is, again, I printed the number of times this model ran. So it, again, each line that you see is like a new set of model. So this is the parameter that it ran on, and it had the accuracy of like 0%. Whereas with this parameter, the accuracy was 88%. So multiple models were created, and we chose the best model at the end of the day, which is like 89% accuracy. So which one of you think like 89% accuracy is good, right? Anybody? Like a model, like almost 90%, right? It's able to predict things correctly. So does it mean that the model is doing well, right? So I don't think so. So accuracy is just like one aspect of understanding the model. So think about this. So in an airline industry, again, Chris could remember this. This is an example that one of our professor gave to us, like for machine learning. If you are building a machine learning model for airport screening, like tens and thousands of people are like good people, right? They are not terrorists, but there is just one or two people who very rarely show up who might be a potential terrorist. So if we had to build a model to identify, like, of all these people that are traveling through the terminal, identify that one person who might be a threat to the national security.
Yeah.
Right? Sorry, go on.
I was going to say it's an imbalanced classification problem, right? So this is a good example of when you have a majority class, which is, obviously not terrorist, but you have a minority class, which is a very small segment of people, and you want to predict essentially, does a person belong to that minority class of, A being a terrorist or A being a threat? This is an example of an imbalanced classification problem. So I just wanted to throw that out there.
Absolutely, yeah. So in this case, right, just by looking at the model performance, my model would probably be able to predict like 99% accuracy that like all the people that I'm screening are not a terrorist. But for whatever reason, this 0.1% model error, right, that could lead into identifying or invalidly or misclassifying a terrorist as a good person and letting them into the airplane, right? So we do not want to make that happen. So just the accuracy, right, at time doesn't help. You need to dig a bit more than that. So so let's look in terms of like how what are the factors that we could use to understand, like, how well the model had performed. So in this case, again, this is a chart that we also showed in the presentation. So this model is overfitting. If you see, it started learning very well at the beginning, but as we, as the model was training, right, it was sharply, came to a point, right? But the learning rate, if you see, it's kept increasing a little bit. It's not much, right? So it was 0.025, yeah. So it started at 0.025 and came at 0.1. So the learning rate is a little bit higher compared to where it started, but it's a little bit higher as well. If you see the validation, which is like a testing at the end of the day, right? The loss is very high, but then it eventually zeroed in on the prediction like way too quick. So this is a classic example of like an overfit model where a model is has learned or is learning very well the training data set, but when you present it in the real world scenario with a different data set, the model performance would not be that great. So this is like we have basically this is like a high variance, right? So this is not good. Likewise, I tuned the model, again, the same data set. I tuned the model a little bit, and this is what I get. I miss, I think, overfit model. Where is the underfit model? So, okay, this is good fit. Okay, anyway, I don't know. So I don't know where the underfit model is. Okay, so this is a good example of like a good model, right? So where the training loss was very high at the beginning of the training session, because that's when the model is seeing the data for the first time. It's trying to make sense out of it. So it is. So it's reducing the loss at some point in time. It's learning something different. So loss goes a little bit high, but as the iteration goes on, as it sees more and more data, the learning curve is plateauing, right? So this gives a good sense that the model has learned enough data points, and it's able to generalize the data enough such that it's able to predict correctly or when it sees a new set of data. The same applies here in the validation as well. Like it starts the loss starts at very high number, and then it as the data, like other model traverses through the data, the loss kind of keeps decreasing, but at some point in time it hits the plateau, and this plateau is very close to that of what the model saw during the training example. So this is the kind of model that we want to ideally build at the end of the day. So this is how we do the bias versus the variance trade-off, right? You build the analytics like this, run multiple models, right? It's not in machine learning or artificial intelligence, it's not just like you build a model and that's to deploy. So you have to build many models and then compare the performance and some of this analytics out of it, and then build or pick on the one best fit model that would meet your need. So what I'm showing here is a classification problem. Chris, do you want to add anything before I move on to a regression?
No, I think we're good. Might want to do some questions though, just because we only got 2 minutes left. But yeah, Anthony hit the nail on the head, right? This is in terms of this is called like the model development phase, but specifically model selection, where you're comparing different models, and what you're doing is you're comparing different models of the same class with different like parameters, different tuning, and you're probably also comparing models of different classes, and whatever one has the best performance is usually what you want to deploy. But then, as you mentioned before, you want to monitor that deployment, just because with traditional software deployment, things are more static, but with machine learning models, you have the aspect of data and you have the aspect of data changing, and that can cause model degradation over time, depending on kind of how quickly the input data that the model is being exposed to changes. and in which case
Right.
you'd want to do this whole process again. But if this process is automated, then that can kind of compound the difficulty if you're not being vigilant of certain bias or certain errors.
Yeah, with that, we can open it up to question. So again, this is like a regression problem. Again, this is like a high bias, high variance. So the model that we want to build is something like this. So this is something that Chris covered in his presentation.
Yeah. Are you able to share your code with them as maybe like a Google Collab? Okay, because I have a code snippet too, and I'll share it in the comments. I don't think we're gonna have time to go over it, but both of us can kind of share our code snippet, and they can maybe take a deeper dive into some of the code. And I see you've got comments, which is good. So I think that'd be a good idea.
That's great. And I'm curious, so first of all, does anybody have any questions? And also, or alternatively, does anyone have anything they'd like to share in terms of like reflections or how this information might apply to the projects you're working on? You can also feel free to drop it in the chat if you're feeling shy. Angel says, are the slides available to look over?
Yep.
Yes. I don't see why not. And it's more of a thing for you, Anthony. Would you be able to share the slides with them?
Yes, I'll share it with you, Jacob and Ryan, both the slide and the code snippets. Yep.
Perfect. So we'll be sending a follow-up email, Angel, and for everybody with that information, as well as there will be a recording of this presentation as well. So if you missed anything from the actual presentation, that'll be on our YouTube channel, which we'll share in just a moment.
All right. Hi, this is Stephanie. I have a question. Well, yes, I have a question. Next month, I'll be presenting virtually at a conference called Data Justice, hosted by the University of Cardiff in Wales. And my topic is bias in AI and the, I guess, the ethical responsibilities of developers. What are their responsibilities that they have when they're building tech that ultimately becomes like a tool of state violence, like for example, with facial recognition. And so I guess I was just wondering, I was interested in this talk because I wanted to know, like from a technical aspect, how, I guess, how can some of these approaches be applied to that?
Right. It's a great question.
How can you apply this to addressing that question?
Right. So the first thing that any data scientist should realize is that like they as a human, right, they have a bias like within themselves, and the data that has been collected is biased, right? So first realizing that our world is not perfect, the data that I'm getting is not perfect, right? There are some inherent issues within the data, and within my view of looking at the data, that is very important, right? Acknowledging that there is an issue. So once you acknowledge it, right, then, like I said, 80% of the work lies on understanding the use case. So you should have a good knowledge on what problem you're trying to solve, as well as understand the data value. Like you would be presented with list of data sets, right? Understand the data sets that you have, like each and every single data element, have a good understanding of that. Some of the data, right, once you start understanding it, you might realize, like, the example that I gave, like to measure the sexes, right? Do we really need the gender column for the model prediction? You don't, right? So you then assess like what data elements you need and how you can, or if at the end of the day, if you realize, like, I do need some other data element for my model to not be biased to a certain group or a certain gender, then you might ask for more data element. Or at times you could choose to eliminate few records itself, like if it is not representing the world correctly. But for all of this, right, you need to have a good understanding of the business domain that you're working on. It. If you do not have them, then that's fine, but you should at least work with someone who has a good understanding and the grasp of the data, right?
Yeah.
So that is the first thing. So Chris, go ahead.
Yeah, I was going to piggyback on that. It definitely pays a lot of dividends to work with like a subject matter expert for whatever the domain is. And I mean, detecting bias is hard. Removing bias is probably even harder. I think some of the techniques we went over in the PowerPoint, like the explainable AI and some of those tools, for example, SHAP and Lime for one, showing you why or how a prediction was made. So if a model makes a prediction, then those tools can kind of debug it and say, hey, these are the particular predictors and features that led to us making this prediction. So that's one way, having interpretable models, having explainable models. Another way is just increasing your data diversity and increasing your data representation. So if you have like, I don't know, a very imbalanced ratio for a particular data set, for example, like a crime data set, and you have a lot of groups that are maybe underrepresented or overrepresented in that, it can go a long way in terms of making a better model if you focus on adding additional data for those underrepresented groups or increasing the data diversity. And then even, I think we went over in this, we had this in the slides, but we didn't go over it too much, using other metrics too, right? Accuracy isn't always the best metric. There's other metrics you can use, like precision and recall, which will give you a better indication of if your model is underperforming on a certain subsegment of people. So those are three things you can do in terms of like diagnosing that bias exists, and then maybe doing something prescriptive to help make a better model that is less susceptible to that kind of bias.
Hey, this is Steve. I will say I started collecting examples of bias in AI back in 2019, and I've been sort of accreting this list over the past couple of years. And one of the things I've noticed is it seems like the vast majority of instances of bias tends to come from biased data sets. It seems to be an extremely tricky problem to address. Particularly, one of the things you just mentioned, Chris, was looking out for certain groups being overrepresented or underrepresented in the data set. That can be a really difficult question when you ask the question, how do you define proper representation? You know, taking crime, for example, if you look at racial representation in the crime data set, if you're defining proper representation, for example, by the proportion of different races that are currently incarcerated, you're just going to end up encapsulating a lot of the bias and racism that's already inherent in the systems. And so it can be really tricky, I think, to define proper representation, and you can have really weird things that lead to biased data sets. For example, I think there's like a genomic study done in Norway or Finland or something like that, where they did a survey of the citizens of the country. So for their purposes, that should lead to a fairly even representation of their citizens. But because of the details of how they did the survey, you had to come in and contribute, you know, a blood sample or something like that. And it was during business hours, which meant typically the only people who volunteered were the people who could afford to take off in the middle of the day, or maybe worked at home because their spouse worked, which then leads to the data set being represented by more affluent people throughout the country, and pretty much no representation of people who, you know, work, you know, from 9 to 9 and then go straight home to watch their kids or something like that. And so it's just
that's the kind of sample bias. That's a really good example of like sample bias, for example, where it's almost like survivorship bias too in that case, to where only the people that I guess were affluent enough and had the time were able to even participate in the study. But it's definitely a tough problem, and it's not as easy as just removing a feature too, right? If you have a predictor like age or gender, and you think, okay, let me remove this, my problem solved. Not necessarily, because, for example, like zip codes can reflect a lot of systematic bias in terms of access to particular kinds of housing. So I think having interpretable and explainable models is probably maybe the best solution we have right now. And the cool thing about SHAP and Lime is that you can use those with some of those black box methods like neural networks and ensembles that do provide that awesome lift in performance. And at the same time, you can use those techniques to maybe get a better understanding of why it's making a prediction like this. But it's certainly a very difficult problem. And that's probably the biggest barrier for why machine learning is not as widely adopted in finance or healthcare or some of those other fields to where it has the most promise. But yeah, that's a really good question. I think a really good point. Thank you.
Fantastic. Just in the interest of time, thank you everybody for sticking around a few extra minutes. This was fantastic, Antony and Chris. Thank you guys so much for sharing your wisdom and kicking off a really big conversation in pretty remarkably simple terms, given how large this topic is. I would love to keep this conversation alive. I think there's just so much more to dive into and discuss. So encourage everybody who is present to keep in touch. We will definitely be doing more similar types of topics in the near future. So we'll keep you posted. Again, we'll be sending out a follow-up email. Also include you to get connected with the links that we've shared in the chat. And those will come via email as well. I'd love to maybe even, I'm thinking we could start like a data engineering channel in the Slack chat so that we can just keep this conversation grooving in between presentations as well. Yeah, that's another thought there. But in any case, thank you so much for everyone attending. Again, the session was recorded. We'll be sharing that recording in the near future. And we definitely hope to see everybody soon. Please don't be a stranger. We'd love to chat with you.